Hello, everyone. I am Tianxin Xu, and I am honored to present our latest work, MBPTrack, Improving 3D Point Cloud Tracking with Memory Networks and Box Priors. The ability to track objects in 3D space is essential for numerous applications, including robotics, autonomous driving, and surveillance systems. However, it remains a challenging problem due to the following four cases occurred in real traffic scenes, including the large appearance variation of the tracked target caused by limited sensor resolution, widespread intraclass distractors, target disappearance caused by occlusion, and the substantial differences in size and geometry across the various categories of tracked targets. Despite achieving promising results on popular datasets, previous methods such as CXTrack and M2Track only takes part of these issues into consideration. In contrast, our proposed MBPTrack addresses all of the aforementioned issues by exploiting rich spatial and temporal contextual information contained in the point cloud sequence and the given box prior. We follow the paradigm proposed in CXTrack to predict the 3D bounding box of the target frame by frame, which directly takes point clouds from the frames as input and predicts the status residual between two consecutive frames. In contrast, MBPTrack also leverages rich spatial and temporal contextual information in historical frames for better localization. The overall design of MBPTrack includes a hierarchical feature learning architecture to embed local geometric features, a decoupling feature propagation module which relies on memory mechanism to explore contextual information in historical frames, and a novel box prior localization network to obtain high-quality target proposals. To leverage both spatial and temporal information from the past frames while propagating target cues into the current frame, we introduce a decoupling feature propagation module, DEF-PM, into the 3D SOT task, which relies on a memory mechanism. It decouples the propagation of geometric features and mask features into two parallel branches with shared attention maps, because integrating targetness information will inevitably cause the loss of object-agnostic geometric information. To tackle the difference in size and geometry among the tracked targets for precise localization, we propose to sample a set of reference points around each predicted target center and then obtain a 3D dense feature map from unordered point features. Despite the simplicity, reference points have the following properties, which can significantly benefit the localization task. First, reference points can serve as a coarse prediction of the localization of targets. Secondly, by leveraging size information, reference points make the network adaptive to targets of different sizes. Thirdly, for targets such as vehicles that have simple shapes, reference points provide a strong shape prior, which roughly cover the targets in 3D space. Extensive experiments on KITTI datasets show our method surpasses previous state-of-the-art on tracked targets of varying sizes while maintaining high efficiency. Here are the experimental results on nuScenes and Waymo Dataset. Our method achieves a consistent and large performance gain compared with previous work on more challenging datasets. We also present a visual analysis of the tracking results on KITTI. It can be observed that our method achieves promising performance in the cases of large appearance variation, target disappearance, and intraclass distractors. MBPTrack predicts the status residual between two consecutive frames. Thus, it may fail to predict an accurate orientation of the target if the orientation of the 3D bounding box in previous frame is very inaccurate. Besides, even for humans, it is difficult to determine whether the points in the fourth image belong to the left or right side of the car without consistent motion information. In the future, we would like to explicitly model the target motion to address this issue. The code is open source on GitHub. Thank you for your attention.